Okay, this video will cover the review questions from Chapter 16, typically to be included on Exam 3 of my courses for General Chemistry 2 here at York College. So if you've got your review sheet handy, depending on the numbering, look around. The first question that relates to Chapter 17 is one that says, calculate the standard entropy change for the combustion of methanol at 25 degrees Celsius. So that's where I'm going to begin for these problems. So methanol, the reaction is 2CH3OH plus 3 oxygen, producing 2 carbon dioxide and 4 water. To calculate the entropy change for this reaction, we would use Hess's law. And the standard entropy change would be found by summing up the standard molar entropies of our products and subtracting the sum of the standard molar entropies of our reactants. So these are supplied, or you'd find them in an appendix in your book. But for this reaction, that would be 2 moles of carbon dioxide, whose molar entropy is 213.7, plus 4 moles for water, 188.8 in its gas phase, as it is in this reaction, although I haven't shown the phases, minus 2 moles of methanol at 127.2 joules per mole Kelvin, and 3 for oxygen, 205.1. So, quick calculation here. 2 times 213.7 plus 4 times 188.8, subtracting 2 times 127.2 and 3 times 205.1 leaves us with 312.9 joules per Kelvin as the standard entropy change for this reaction. Right. Now, let's just extend here for a second. A positive entropy change is generally associated with a process being spontaneous. That's a favorable outcome in that we are making the system less organized, and that in terms of the universe's entropy at least is a favorable process. So we're asked to do really the exact same thing for our next reaction. Our next question is 2 mercuric oxide, 2HGO, to give us 2Hg and an O2. So the standard entropy change would be 2 times the value that we're given for mercury, which is the 76.0 joules per mole Kelvin, plus oxygen, again 205.1, minus 2 times the mercuric oxide value of 70.3. So 2 times 76 plus 205.1 minus 2 times 70.3. And we come up with 216.5, again with a plus sign there, joules per Kelvin. Next question asks about the changing nature of a chemical reaction. The question is, at what temperatures will a reaction be spontaneous if its delta H equals a positive 158 kilojoules, and if its delta S equals a positive 411 joules per Kelvin. So for what range of temperatures will this reaction be spontaneous? This answer comes from solving from the Gibbs free energy. We know that when the Gibbs free energy is negative, our reaction is spontaneous. And that behavior can change with temperature if H and S have the same signs, as they do in this case. So the transition temperature is found by setting the delta G equal to 0 and that's delta H divided by delta S. Now H and S have slightly different unit sets, kilojoules and joules, with respect to energy at least. So we have to match those up, 158 kilojoules divided by 0.411 kilojoules per Kelvin. Okay, we get a transition temperature of 384 Kelvin. Now, for what range is this reaction spontaneous? Now we want to think about all the possible values of temperature from 0 to infinity. 384 has just become the dividing line. On one side of 384, this reaction will behave one way. On the other side, it will behave a different way. So what we need is a test. Why don't we test 300? It's here on the left, below 384. So let's test 300 Kelvin. Delta G at 300 would be 158, delta H, minus 300 temperature times the 0.411. Or positive 34.7. Therefore, delta G is going to be greater than 0 for all values on the left side here, below 384. So it's non-spontaneous there, spontaneous here. The answer to the question then is, this reaction will be spontaneous for all temperatures greater than 384 Kelvin. A different way to arrive at the same conclusion would be to look at the sign of the enthalpy change for this reaction. Plus, it's an endothermic reaction, which means it needs energy, i.e. temperature, to drive that reaction. So, obviously at higher temperatures, you're going to have more energy available to drive that reaction, and that's what will make it spontaneous. Okay? So, sort of a qualitative or conceptual way to arrive at the same answer. Okay. Now we move into some questions about free energy. Calculate delta G for a reaction at 25 degrees Celsius. All right. And we're supplied the delta H and delta S. So the delta G is simply Gibbs free energy, the enthalpy change minus temperature times the entropy change. So we're given the enthalpy change of positive 442.4 kilojoules minus the temperature, which I'll convert to Kelvin, 298 Kelvin, times the entropy change, positive 206.9. That's in joules though, so I'm going to convert it 0.2069 kilojoules per Kelvin. Again, so that I can add those two kilojoule quantities. After I multiply these two, this is a value of kilojoules. So 442.4 minus 298 times 0.2069. This delta G is positive 380.7, okay, or 380.7 kilojoules. So this reaction is non-spontaneous at 25 degrees Celsius. As an endothermic reaction, again, following up what we just did here, this reaction will become spontaneous at higher temperatures. As we go to higher temperatures, we're getting paid an entropy bonus, so to speak. So we need to go to higher temperatures to overcome the endothermic change in bond energies here. Okay. A few left here. Another calculate a delta G for a reaction here. This time the reaction is iron and chlorine, produce iron chloride. Two Fe plus 3 Cl2 produce 2 FeCl3. We're asked to calculate delta G, but unlike the previous problem where we were just given the delta H and the delta S, we're given delta H formation values for these compounds. Now I'm going to write them directly underneath. So 0 for iron, 0 for chlorine, negative 344.0 for FeCl3. And then we're given S0 values, 27.78 for iron, 223.08 for chlorine, and 142.3 for iron 3 chloride. Okay. So what we need to first do is calculate delta H for the reaction. So if we're going to calculate delta G for a reaction, it needs to depend on delta H for the reaction and delta S for the reaction. So not just a single enthalpy of formation values. That's why the subscripts are important, and paying attention to them can be very critical in solving the problem. So I'm going to use Hess's law. Sum up the enthalpies of formation of the products minus the enthalpies of formation of the reactants. This is a nice reaction in that for this one at least, the reactants are 0. So it's just 2 times negative 344 minus 0. So the delta H is negative 688.0 kilojoules. We can apply the same formula to entropy, but now we've got numbers for the reactants. So 2 times 142.3 minus 2 times 27.78 plus 3 times 223.08. Two times 142.3 minus 2 times 27.78 and minus 3 times 223.08. Negative, oh, I made a calculator error here, that didn't look right. 2 times 142.3 minus 2 times 27.78 and 3 times 223.08. Now we got negative 440.2 joules per Kelvin. So, delta G is found now by delta H minus T delta S. Checking our temperature, it is 25 degrees Celsius again. So, our delta H, negative 688 kilojoules minus 298 Kelvin times negative 0.4402 kilojoules per Kelvin. Again, usually it's my entropy that's significantly smaller on the joule scale, so usually it's the one that needs converted. And I come up with a negative 556.8 kilojoules as the free energy change. Highly spontaneous because that's a large negative value since reaction is very spontaneous. Okay. Just 2 questions left. Now these are going to relate to free energy and equilibrium, the connection between those 2 concepts. The standard free energy change is negative 18.3 kilojoules per mole. What is the equilibrium constant at 87 degrees Celsius? So the equilibrium constant, KEQ, is e to the negative delta G of a process divided by RT. So it's going to be e raised to the negative, now I'm going to convert 18.3 kilojoules to 18,300 joules per mole, so that when I divide by my value for R, whose units are joules per mole, I get the unit cancellation that I need. Just like here, I converted, one to the other. It doesn't matter which way you go. You can convert the joules to kilojoules or the kilojoules to joules. Here, I've converted the 18.3 kilojoules to joules. I do need to multiply by my temperature, My 87 degrees Celsius, I add 273, that's 360 Kelvin. The two negative signs are going to cancel out. We're going to have 18,300 divided by 8.314 and 360. I've got e to the positive 6.11 power. So 450 or 452, but for 2 sig figs, for the temperature, that's probably fine. So this is our equilibrium constant, KEQ. Right. Still fairly, it's a fairly big equilibrium constant. It's bigger than 1. So this is a product favored reaction with a big equilibrium constant. And that also agrees with the idea that this was a negative free energy change. So it's a spontaneous reaction, a system that will move from its reactant side to its product side. And the last question on this review sheet, we're given the equilibrium constant, what is delta G? So the inverse of this formula, when we solve it for delta G is negative RT times the natural logarithm of KEQ. So that's going to be negative 8.314 joules per mole Kelvin. Our temperature here is 25 degrees Celsius, so 298 Kelvin, times the ln of 4.7 times 10 to the minus 8. This is a small equilibrium constant. That means it's a reactant-favored system. And so in terms of spontaneity, this is not going to be a spontaneous reaction. I expect a positive answer here because this equilibrium constant means the reaction system prefers its reactant side. So it wants to stay there. It does not want to move over to the product side. So nothing's going to happen, i.e. non-spontaneous. All right, ln 4.7 times 10 to the negative 8. I'm actually starting at the right-hand side there. Then multiplying that by the 298 and by the 8.314, I get 41,800 joules per mole. So if I put this into kilojoules, which would be appropriate given the scale there, that's large enough, the free energy change of this reaction is a positive 41.8 kilojoules per mole. Again, that means that this is not a spontaneous reaction. Right? So we've addressed the several examples in this chapter 17 relating to free energy, entropy, and the connection to equilibrium constants, and had a pretty good overview of the types of problems you would be able to expect to see on an exam. All right? Good luck. If you have questions, as always, follow up and ask me in class.